Yeah, hello, welcome to our last session in this stream of JCON 2020. And the next session is about in-memory computing, the big picture. My name is Markus Kett. I'm CEO of MicroStream. And yeah, I came to programming with about 30 years ago, or even longer, programming with the C64 with assembler. So in-memory computing, I always loved in-memory computing and assembler. And yeah, some years later, so about 20 years ago, I came to Java, and since almost 15 years, we have been developing developer tools for Java developers. And we developed with our team together two Java IDEs, and since about 6 years or so, we have been working on the JBoss Hibernate Tools for Eclipse and have always tried to improve these tools. And here are some screenshots about the Hibernate tooling in Rapid Clips we have worked on. So when I talk about object relational mapping, sometimes then it sometimes sounds like I don't like Hibernate or so. But this is not true. I have to say that because I have been working on these tools together with my team a long time, and object relational mapping, of course, is with Hibernate the best thing you can use for for storing objects in relational databases. So, but there are challenges, and the last years I spent to improve these issues, and this is what we do in MicroStream. But later, more about MicroStream. This talk is more about the big picture of in-memory computing, and all around the world, the more and more companies, they have to collect more and more data, or they want to collect more and more data. And they have to query the data and to connect the data and query it in almost in real time. This is more and more important for these technologies and solutions of the future, like IoT or AI, machine learning, virtual reality, and so on. And the amount of data increases more and more. So performance is more and more super important for our solutions. And the big question is, are our systems really fast enough? Is the programming language fast enough? Is Java fast enough? And are the database systems we use today, are they fast enough to develop such kind of like application solutions for the future? And of course, with memory computing, we can accelerate our systems tremendously. And so this is the reason why, of course, we all should use memory computing if possible. But in practice, there are a lot of confusion about the memory computing. So the question often is, what actually is a cache? What's an in-memory data grid? And what is the difference between in-memory data grid and a distributed cache or in-memory database? And when should I use a memory database? When should I use a data grid? Or are there other approaches? And this talk gives you an overview, and I like to explain a little bit the different architectures and talk about the differences and what application or what solution could be a good, is suited for your application. Why should we use memory computing? What's the problem in our systems? Why we need or why we want to use memory computing? There are different aspects. One is, for instance, the relational database. It was the standard, or it is still the standard, of course, since decades. We use relational database systems. But we all know it, and it's discussed at many developer conferences, and even at the Oracle Code Conference, we had talks about the future of databases. Are relational databases really fast enough for the future? Then we have sometimes performance issues when we have access to hard disk drives. We know that hard disk drives are, in comparison to memory, are super slow, and we should avoid accessing a hard disk drive. So it's better to have access directly to memory. And of course, the network is one of the biggest bottleneck in our applications. And it's not only the latency. By the way, it was very interesting. I read that Amazon, they found out that 1 millisecond in latency costs them $1 million in business. So this is very interesting. So latency is really expensive. And almost for all companies using the cloud today, they often run out of money with their cloud costs in the cloud. So the costs in the cloud increases more and more. And then we have the complexity. So for the developers and for the DevOps teams, its complexity is often a problem, a topic, and the challenge, of course. So this is the reason why we should use in-memory computing, and we can really improve our systems with in-memory computing. Let's have a look about some numbers. Here we can see access to a hard disk drive mostly takes milliseconds. And for human, milliseconds is super slow. Sorry, milliseconds is fast, but for computer, it's super slow. We can see access to a DRAM, for instance, is incredible faster. So we have your access time in nanoseconds. And I've learned in assembler, when we execute an instruction, then it only takes nanoseconds to execute this instruction. So this is up to 100,000 times faster accessing DRAM in comparison to a hard disk drive. And the CPU cache is almost faster. Here are some additional numbers from a Git side, latency numbers every programmer should know. And for us here in this talk, the most interesting numbers are accessing time to the memory here. Reading, for instance, 1 megabyte takes 250 microseconds. And when we read the same amount of data from a hard disk drive, takes 20,000 microseconds. So we are with in-memory up to 80 times faster than accessing to hard disk drive. And yeah, there are many opinions, and many people say the best access to a hard disk drive is when you don't need it. So it's you should avoid it, and you should access to in-memory when possible. Where is the bottleneck in our application? Mostly, and now we have to talk again about object relational mapping, because this is one of the important things and one of the really most important reasons why our systems often so slow when we have access to databases. The reason is in Java, we work with objects and with object graphs. And when we want to store data in a relational database, then we have to map our objects to the database data structure. Then we have to map our objects to tables. And from a technical perspective, this is actually not possible to store a complex object graph into a flat table. So we are in trouble. But of course, the Java architects, they solved this problem. And now with object relational mapping frameworks, we have solved this problem. Now we can use it so it works in practice. Now we can say we are able to store objects in a table, but actually this is not really true, but well, it's actually a conversion of data behind the scenes. We cannot store the object, but we can convert it and then it works. And it works in practice. We can do everything with it, but conversion of data takes always lots of computing time. So imagine you want to, for instance, convert a video file or so. And sometimes it takes minutes, sometimes hours. So this is the reason converting of data takes lots of computing time. So we should avoid to do that, actually. Yeah, here we can see the architecture of today. Here is Java application in the relational database, and between the application and the database, we have this orange box, and this is the object relational mapping framework. You know, Hibernate is the standard, de facto standard here in the market, and it works. Then some years ago, the NoSQL databases came up, and the big question since years is, are the NoSQL databases now better? Or why should we use NoSQL databases? And when we have a look on the different solutions, then we see there are many differences between the NoSQL databases, and they provide different data structure. So because the vendors maybe were not convinced that the relational model, the table model, is the perfect model, so sometimes a different data model is a better fit. So okay, let's use a JSON for instance. Yeah, but there's also, it's not possible to store a complex object graph directly into a NoSQL database. So you have a mapping here as well. So we have actually the same problems, the same core problems. The reason why this is my personal opinion is that the NoSQL databases are so successful because they are now able to scale horizontally very easily. It's much easier than the table model. This is not suited to scale horizontally. So with a relational database, actually, we are able to scale vertically. And yeah, as long as we have this incompatible between the Java objects, the Java object oriented world and the database world, which is totally different. As long we have this incompatibilities, we have these challenges. So the systems increase from the complexity more and more, or we lose performance. So we cannot solve this. If we want to solve this, we have to eliminate the core problem. Yeah, here we can see again a JPA architecture. We know relational databases maybe are not fast enough for our system. What can we do? The common way is, hey, let's use a local cache. And in Hibernate, we call it the second level cache. And then we can avoid reading the data from the database because all result sets are stored in the local cache, and when we execute the same query again, then the data can be read directly from cache. And we saw the numbers. Access time to memory is super slow. It's super fast. So I would expect now we have microseconds access time when we read data directly from a cache. So good decision. And but in our in this picture we can see the cache is an additional layer on top of the mapping framework. So the architecture gets more and more complex. Okay, but now we have faster results, and it works very, very well. But be careful with caching. It sometimes is a little bit tricky. So you can. It's always a challenge to configure the cache. But this is it's another topic. What we can do is we can also use an in-memory database, because when we read the data from cache, then we get the result set from a previous query. And sometimes it would be cool if we could query the data in memory. And this is the idea of in-memory database. So okay, then let's move the database system directly in memory. Then the entire database management system runs directly in memory. And so we are able to execute SQL directly in memory. And this is very cool. And the advantage is here, or one of the advantages is here, we can use SQL. Then we don't have to change our applications for that. So if we have already a relational database, then it's very easily to add an in-memory database to your application. And if you use already a relational database, of course, then you're familiar with the technology, the administrator, everything is the same. It's pretty much the same. Yeah, and it's well suited if you have existing businesses like ERP, CRM, or data warehouse system, or you do business analytics or something like that. And as I mentioned before, the in-memory database, the relational in-memory database is suited for scaling vertically. Yeah, let's get back to a common GPU architecture. Now, what we can do is, when we use a cache, then sometimes scaling vertically is not always the best fit. And our dream is to have more memory. So the idea is, okay, I give you the memory you need. You can have unendless memory if you like. Then use a distributed cache, because now with a distributed cache, you can share the RAM of your machine over hundreds or thousand nodes if you like. Then you can scale your memory of your machine over hundreds of nodes. And then you can store your data in memory, and it's super fast, and you can accelerate your application. Maybe you know solutions like Redis, Coherence. You can use as a distributed cache, cache, for instance. But now what we can see is here, in comparison to the local cache, we have here network latency between our application and the memory. So actually, it's not as fast as the local cache, right? But this is the problem we have here in this architecture. You have to see, is this suited for your application? Then use a distributed cache. It's a good fit for many applications. And here in this game, Redis is very popular and very often used as a distributed cache. Yeah, but let's copy our nodes in a distributed application. Then more nodes want to have access to the distributed cache. And this is a common architecture now in a distributed world where everything is scalable, horizontally scalable, distributed, and high availability. But now the architecture looks pretty much complex, but we can increase our complexity again because maybe you want to cache some data in the nodes, so you can add here again a local cache, and so then our architecture looks like that. A distributed cache is very flexible. You can scale it horizontally over hundreds or 1,000 nodes. And the scale out is fully automated. And so this is very suited if you have an application that mostly it's boring for the application, nothing happens. But then if you have a shop system, for instance, especially on one day, Black Friday, then you have a lot of traffic and then you need computing power for only one day or so. Then you can scale your architecture, your memory, scale it over hundreds of nodes. And on Saturday, when it's over, then you can, you can run your shop system again on only 2 nodes or so. So, and it's highly available. The data structure mostly here is a key value store. And the data, of course, are not persisted here. So we use it for reading the data only. If you want to store data persistently, then we go back to the database system, to the single source of truth. And then we can see that actually the common database is only used for persisting the data as a kind of like backup strategy. Reading access only to the in-memory distributed cache. What else? An in-memory data grid is pretty much the same like a distributed cache. You can do the same stuff with in-memory data grid. And this is the reason why the architecture looks very similar. But we have with in-memory data grid is some additional computing functions. So more computing power on top of the nodes. And in comparison to a distributed cache, in a distributed cache, you only cache the data, that's it. With in-memory data grid, you get additional computing power on co-located processing, etc., something like that. So this is the most difference. And here we can see the architecture is very similar to a distributed cache. And so the advantages are also very similar. You can use in-memory data grid for scaling horizontally over hundreds or 1,000 nodes. The scale out is automated. And you can support, and all kind of applications are supported. So the grid is high available. That means the data are not only stored in only one node, it's shared over 3 or even more nodes. So if you lose one node, it's not a problem because it's replicated behind the scenes automatic. And this is also very similar to a distributed cache. Persistence is you can persist your data with by using the common relational database behind the scenes, or you can persist also single nodes with serialization, for instance. Okay. We have seen that we still have a network latency. We have network between the application and the in-memory data grid or the distributed cache. So it is not as fast as it could be. It's not as fast as local RAM, as local cache, of course. But what I have not expected is that actually the local cache is not as fast as I would expect as a previous assembler programmer. Because when we measure the time, how long does it take to read data from the cache? Then sometimes it's very slow. It's also milliseconds instead of microseconds. Why? It's because the local cache does not store the objects as we use it. So when accessing the cache, then the relational mapping framework has to generate objects here again and here as well. So even when we have access directly to the memory, we have object relational mapping behind the scenes. That means conversion of data. That means we lose lots of computing time. And this is the reason why JPA applications using local cache sometimes are not super fast and feel slow and lazy. It's because of the need an object relational mapping in any case. With MicroStream, we have a completely new approach, and I'd like to give you only a short introduction to MicroStream. With MicroStream, we can store object graphs, and we are convinced that we can boost in-memory computing dramatically. Why is this possible? Because we believe that Java is the perfect in-memory technology, and it's made for in-memory computing. We have the perfect data structure. We have objects. We have the object graph, and it's built for. It's kind of like a multi-model data model, because yeah, you can use any Java type. You can store single objects. You can use collections. So you can use any data type you like in an object graph. And you can design it freely. And it's in memory and it's managed by the JVM. But in addition to that, Java provides us a perfect query language. For instance, Streams API. And with Streams, you can query object graphs, and this is always super fast. So if you query a complex and huge object graph, it will only take microseconds. And this is even much faster than reading directly from a local Hibernate cache. We have measured that and we have proven that, but you should also check it out, prove it up. This is if this is really true, what I say, but it is definitely, because there is no generating of objects behind the scenes. The object graph is already here. We only have to query the object graph. And even if you have lots of data in the object graph and you have go through all these nodes of an object graph, doesn't matter. It's fast enough. It's super fast and even faster than reading data from a local cache. And I have a performance demo that proves that. I hope this will work this time with the third attempt. And the query language and the streams API, of course, are type safe. So it's perfect for Java developers. And with these tools, with an object graph and a streams API, you can get out actually like a local cache. So you can replace your local cache, and with the streams API as a query language, it works like an in-memory database, but with pure Java features, and it's core Java only. And you can use it out of the box. Everybody's familiar with this. The only problem is Java does not provide a native function for storing object graphs. And we added this function to Java. And now we go open source with that. With MicroStream, you're now able to store any object graph, any complexibility, any Java types you use. You can store really every object graph. And you can decide what you want to store. If you want to store a single object, or you want to store a subgraph or the entire object graph. But in practice, mostly, let's click the button, mostly you will store subgraphs. And with MicroStream, you can store it in any database system. We support currently Oracle. And you can use the Oracle Relational database as well as the Oracle NoSQL database. But you also, now you can use any in-memory technology. You can use distributed cache. You can use an in-memory data grid to store your object references. You even can use a blob store in the cloud. And here we support the Oracle Object Store, and we support Oracle Coherence. But we have already connectors to different solutions. When you store your object, then this is transaction safe. And yeah, you can increase the performance with multi-threaded input-output operations. So the more core your hardware provides, the faster is the I/O process. And all data are stored as binaries appended to your storage. So every store is appended. And it's only one method call. It's only a store method you have to call. And it's very easy. You need a MicroStream instance. Maybe you define your storage strategy and the path where you store the data, and then call only one method. That's it. And in the other direction, when you start your application, then MicroStream initially loads the object IDs into the memory, and only the object IDs. This is very important. So then you have the IDs of all your objects of the entire database in the RAM, and it's fully indexed. So it's similar to index in a relational database, for instance. But really only the structure, no data are loaded. You can decide if you want to preload data, but you don't have to do that. And one thing is important. If you have enough memory size, then you can load the entire object graph, the entire database in your memory. Then you have the entire data in memory, and then this is the fastest way to query data, of course. Then it is similar to an in-memory database that runs within your JVM. But maybe mostly you won't have enough memory, or the storage size is much bigger. Maybe you have terabytes of data, then and only 16 gigabytes of RAM, then it's not possible to load the entire database in the RAM, of course. Then preload the data you need, and then use lazy loading for loading only the object references on demand. And yeah, this is also very simple with only some methods to use lazy loading. And this lazy loading is a little bit similar to lazy loading of Hibernate. So you can load your object references lazy. But in comparison to Hibernate, you won't get object copies you have to deal with. The loaded objects or subgraphs are directly merged in your object graph. And this is very convenient. Yeah, this input-output operation is also multi-threaded. So the more cores your machine has, the faster will the input-output process be. What else? Anything else here important? You can see some code snippet with lazy loading. So this is really easy. And then we get this architecture here. Then we only have the object graph in the memory. We can use it like an in-memory database. It replaces the object relational framework and your local cache. You can use it as a local cache, as a memory database, as I mentioned, querying it with streams, and load the data you need lazy in the memory, query the data. You can throw the data away if you don't need it anymore. So you have control of the memory. Yeah, objects that are not used anymore are removed by the garbage collector automatically. So there's no magic. It's everything is managed by the JVM, but you have control of that. So you decide when you want to store data. You decide when you want to load data and which amount of data or objects you want to load back in the memory. And you can decide which storage you want to use a relational database or a NoSQL database, distributed cache, or a blob store in the cloud. You also can use Kafka, for instance, to store objects or subgraphs in Kafka and read objects or subgraphs from Kafka. This is also possible. Okay. This is really the last attempt for executing a live demo in a PowerPoint presentation. And we can see it does not work. I tried it so often, it always works, but in presentation it does not work. So we have to cut this out and you get the video. But you can call this link. You see the link here. So use this link to see what this live demo. And this live demo shows two applications running in parallel. One is a bookstore application. It's a common Java application using Hibernate and cache for a local cache. And the data are when the query is executed the second or third time and so on, then the data are really are read from the cache directly, and then you can see how is the difference between reading the data from cache, from a local cache, and how fast is it if you use Streams API, and the blue bar in the demo is the application with MicroStream and Streams API. And the blue bar is the query time of the object graph, of the Streams API in the object graph. And then you can see every single query is executed sometimes 10, 100, but mostly 1,000 times faster than reading data from EH cache. And this is amazing. This shows and proves how fast Java is, because there is no microstream magic. This is the in-memory power of the JVM, nothing else. And if you use GraphQL, then you can have access, or you can give applications, third-party applications, access to the data. You can use the REST API from MicroStream to have access or give third-party applications access to the storage. And if you use GraalVM, then you can accelerate your application. Yeah, you can even accelerate the entire application. Then you get a native image, a Java program as fast as a C program, and this in combination with MicroStream, then you have the max speed, the max power of Java. And this is really incredible, the performance. But the bookstore demo you can see here is not running GraalVM. We will build a demo application with GraalVM in the next few weeks. This runs with OpenJ9 JVM, but you can expect that if you use GraalVM, then we are much faster. And with MicroStream, you can use it also on Android devices. So this is very interesting for all these Internet of Things, automotive solutions. Then with MicroStream, you can build really super fast applications on mobile devices, from edge to server, and on a server as well. You can use SQLite database for persistent data on the mobile devices, and choose on the server side the database or the storage technology you like. Yeah, you can do so many things with in-memory computing, and MicroStream even proves not how cool MicroStream is. Actually, it shows how fast Java is. And so we showed this demo already to introduce it to many Java developers in Java user groups. And there are so many people, they cannot believe that Java can beat a database system. Yeah, check it out, try it out, and try to beat Java together with MicroStream. Send us the link to your demo. Maybe you will be successful, maybe not. So sometimes some people ask me, maybe there is a use case where the database is faster. Yeah, maybe, perhaps, but don't forget, the database must send the data through the network to your machine, and then you never get objects. And this is the reason you need this object relational mapping. And this takes too much computing time. And here you lose the most performance. And the database vendors, they don't measure the time. They only measure the time how fast their queries are. Their SQL is executed. But nobody measures the time, how long does it take to generate the objects. And this is the point. And what can we do with this performance with in-memory computing? My incredible video showed it already. You can now build everything. You can use it for machine learning, for automotive stuff, AI, and so on. And combine it with GraalVM, it's super fast. It's the perfect Java world. Nothing can be faster. And it's better to write these applications with Java. And we don't want to write these applications in C, right? And I don't want to learn Python. So let's state Java. But if you are not so innovative, so maybe you are interested in saving costs. If you have systems that are much faster than before, think about that. We eliminate the effort of converting the data. So we don't have the need for the computing time like before. So if you build an application with JPA and with the common object relational mapping stuff, then mostly you need many machines to get this computing power you need. With pure Java streams in combination with microstream, every single query is executed up to 1,000 times faster. And this means you don't need much computing power for that. And we have applications in practice running at, for instance, Allianz, the insurance company here in Germany, where we have an application that actually needs a cluster. And today this application runs with microstream on only one single machine in the cloud. And so they save up to 90% costs of infrastructure. And this is amazing. So you will have this benefits in all your applications, all your database applications. And you can combine it with the in-memory data grids. You can combine it with the distributed caches. So choose your persistence strategy. And for developers, it's super cool because we have seen this complexity when we use the in-memory data grids or the distributed caches, and you cache the data in many layers. So the complexity increases more and more. So yeah, and deploying, testing of these applications is very complex. And with microstream, you only have one data structure. You have the perfect data model. You have the perfect data structure. You have only Java classes, nothing else, and no dependencies. So it's only you load the microstream as a Java library via Maven, included in your project, and yeah, you can get started. That's it. Only some methods you have to learn. That's it. And then you don't need a caching anymore. You don't need to learn any query language. So, and there are no limits for. So we do not limit you in the kind you program or write your classes. There are no annotations. There are no interfaces you have to implement on no superclass like the old object-oriented databases. So you cannot compare this. And it's core Java, and we go open source. So run it where you like. Java 8 is required, nothing else. Java 8 or higher, of course. And you can use it with all JVM languages, of course. And with GraalVM, you get, I mentioned it already, the best power Java can provide and have ever provided before. So this is a great combination. Thank you, everybody. See you next year. Bye-bye and take care.